electron meaning that electron to come still, because usually when you say valence band electron, you are talking about electron that's in some state, that field state, right? Conduction electron means that electron in conduction band. And conduction band is equivalent to virtual orbital, that they have an unfilled orbital, right? So these are very good. Just like LCAO MO approach, they are very good for a field state that energy level that already have electron in it is quite easy to do. For unfilled state, like conduction band, they are not so good. They are not so accurate. So this usually that's the limitation of these type line methods. And in this Wigner-Saiz method, you remember your Bloch function depends on a periodic function, and then you have this sinusoidal function multiplied to this periodic function. So what Wigner and Saiz said that okay, let's forget about k, because when you have this function, periodic function does not depend on k, and then you multiply a sinusoidal function that depends on k, right? So what Wigner-Saiz said, okay, let's assume everything is like k equals 0. No k dependency, that's what he said. So it greatly simplified this periodic function, and they use that as a way to generate the structure. So it's a way, it's not so popular for most metal. It's good for alkaline metal. If you are battery people, then it's good because if you have one electron, you can essentially what happens essentially you can treat it like a free electron, because you treat everything the same. You almost take out the periodicity in your thing. So it's like a free electron C. This Wigner-Saiz model, all the k non-zero k become k equals 0, and so you simplify the calculation. And the most popular method is the last one. It's called the pseudopotential method. And you heard about this a lot if you read solid-state physics literature, pseudopotential calculator. And what is a pseudopotential? So I show up here. This is a plot, right? This is my potential as a function of R. Okay, so I'm now focusing on just one atom in my lattice here. And of course, everybody knows the electrostatic force. The potential is 1 over R. It's potential is 1 over R. So like this, right? And for most people, they're not so interested in deep core electronic state. They are more interested in the loosely bound, valence electron, because why? Because you can take this out and you can do things with it. Because you don't need a lot of energy to move an electron from the valence band, right? For example, to the conduction band. So you are more interested in the loosely bound valence electron, so to speak, right? Bonding or non-bonding electron that's out there. You don't care about the core electron because they are just sitting there. They modify the effective electrostatic positive charge that your valence electron see. Thus, you can think of it that way. They're deep core. They are very atomic-like. Okay. So people say, okay, well, why I do all this work to try to get this core on potential correct, and the reason why this is very difficult is because if you're looking at the quantum mechanics, the energy, right, the core orbital give you a big share of your total energy, right, because they are deep down, and they have lots of energy, right. The orbital energy of a 1s electron is much higher than, let's say, a 2p electron, right. So these guys are worried. They don't do much in terms of bonding, and yet they contribute a lot to the calculation of the total energy. And if you are trying to minimize the energy to tell you that, okay, I get the best wave function, this is known as the variational approach, then that's really kind of bad, because you are optimizing the core electron that doesn't involve in bonding really. What you're interested in is outside, is not so deep in the core. So people say then, well, let's try then ignore the core. Let's not worry about the core. We would generate, so from a physics point of view, they generate a potential. They would say that, okay, I don't care so much about the core anymore. All I want to do is that I want to generate a potential curve that's very good on the outside and long R, long radius region, large R region. I don't care so much about the small r region, right? Because I don't care about the core electron. I know I would get the core electron electronic state wrong. I only care about the large R region. So what they do is that they generate an effective potential that is very good at large R, quite extremely poor in the core. All they care about is to make sure the charge are balanced. So in the end, what they got is that it's a potential that kind of look like this. It's a weird looking potential. You actually have about passing like this, and then cut down and then go like this. Right? So this potential, this is totally wrong. Within this limit is totally wrong. But on here is very good. On the large R region, it is perfect. It's perfect to what I want to do. So essentially, this is the pseudo potential is a potential that give me exact wave function outside the core, outside the certain core limit, and this is extremely popular method in physics and in calculating all this electronic structure. And and since electronic band structure are really important only for low energy valence band type structure, you ignore all the core. Okay. So when people say pseudo potential, you should recognize right away that okay, these guys are just looking at valence band. They are not really looking at core band. They are not interested in core ionization. They are looking at valence band. They're good at valence band. Once they start talking about core, you would point out to them, hey, you are using pseudo potential, so therefore inherently your method is incorrect because look at your potential. It's not like this. It's wrong. Okay, but that's okay because if they're just interested in the valence properties, it will be fine. Okay, they just need to know the limit. So here's a calculation based on this kind of structure, calculated band structure by of germanium, for example, and you have all this band gap, you have valence band, conduction band, and calculate in this way. Clearly, it depends on K, right, which is good, which is the hallmark of the electronic. Okay, so hopefully I can impress you of some of these calculations. You are not will not be asked to. You should know the qualitative nature of this method. But of course, it's very involved. If you take a real solid state physics course, then Michelle could probably teach you these things, how to calculate these things. Okay, next I'd like to tell you. So far we've been talking about bulk electronic structure. We've been talking about one-dimensional, two-dimensional, and with the suggestion that I can extrapolate the bulk to three-dimension symmetrically, and then you can get, depending on the physical crystal structure you have, you can generate these complicated-looking band structure in a certain direction. This is, of course, the slice in your entire three-dimensional Brillouin zone that we're talking about. Now, of course, we are talking about surfaces, and if you terminate your three-dimensional bulk structure, cut it in a plane, and you generate a surface, and this surface is a two-dimensional object. And so in theory, then we should reduce from 3D to 2D